Welcome back. This is section 9.7, Conservation of Energy, which is section 8.6 in your textbook. Conservation of energy is part of the first law of thermodynamics, which states that neither matter nor energy can be created and it can't be destroyed. Whatever the amount of matter there is in the universe is constant. Whatever the amount of energy in the universe is constant. You can't pop matter into existence by doing a reaction, and you can't pop energy into existence. Neither can you destroy it. So the only thing that you can do with energy is change it from one form into another. So that's an easy statement, but essentially it's everything that happens in the entire world. Everything is a change of energy. All of chemistry is a change of energy and matter interconverting, all the Legos breaking apart and reforming. Everything that happens in among objects, even down to molecules, are happening as a result of energy changes. So to understand this page in your life means that you don't have to understand everything that exists in the whole world. So I don't think we're going to go that far, but we are going to talk a little bit about changing one form of energy into another. So an easy one to start with is the idea that potential energy will become kinetic. If I lift a pencil off the desk, so lift it up into the air above the desk, and then I drop it, since I put work into that pencil, I've given it potential energy due to gravitational potential energy. When I drop it, it becomes accelerated towards the earth because of gravity, and the pencil will gain speed as it does it. Now, its mass probably doesn't change at all, or very little, I guess, but its velocity changes, and as its velocity changes, you've changed its kinetic energy. So potential energy is then converted into kinetic energy. So a different way of expressing this is that all energy, all potential energy and kinetic energy sum up to be all the total energy that there is. So the total amount of energy stays the same. If you've got kinetic energy that on a roller coaster, your car is speeding up a hill and it's slowing down because the hill is giving it potential energy. So the kinetic energy is reducing and the potential energy is gaining. The same amount of energy that you had at the beginning is what you have at the end. If you reduce any of that energy, say you reduce the kinetic energy, say with friction, the wheels on the track will heat up the track or make noise or spark or something like that, and you reduce that amount of energy, that normally can't be gotten back. The heat energy that you lose to a roller coaster track doesn't go back normally into the roller coaster. A lot of hybrid cars now make use of this fact that if you are wasting, every time you apply the brake, that friction is wasting that energy. Well, so they've kind of gotten smart and used the brakes as actually a way to charge an electric motor, which helps to charge the battery. So you get some of that back. That's why that hybrids get really good gas mileage, because not all of it is being wasted in friction. Some of the friction force of slowing down with your brake is actually put back into stored energy and put back into potential. But in any case, it's all going to always be a total. So potential energy summed with kinetic energy is going to be some kind of a total, some type of a total energy. So if you realize that you had 10 joules of potential energy and it turned into 8 joules of kinetic energy, where did the other energy go? The other energy went to heat. So the friction of the wheels, friction of the gears, friction of whatever is going to heat up those substances, and that energy caused it to heat because work was being done to heat it, and so some of that energy was tapped away as heat energy. But at the same time, all of it added together is going to equal the original 10. So in this slide, I've got a pendulum. If the pendulum is moved all the way to the top and then released, the original has only potential energy. When it reaches the bottom, it's only going to have kinetic energy. When it reaches the top again, it's only going to have kinetic energy. That's it. That's if there's no loss, if there's no friction, which there is. The string moving against the air is going to create some friction. But for the most part, kinetic energy is energy due to speed, then potential energy, and then it comes back to kinetic. And then anywhere in the intermediate section is going to be some potential, because it's still got some height to fall, and kinetic, so it's got some speed. And so there's going to be a sum. So if this is 10 and this is 10, then this is 10 plus 0. Potential energy of 10, kinetic energy of 0. Kinetic energy of 10, potential energy of 0. Here would be something like 5 and 5. 5 joules of kinetic energy, 5 of potential energy. And they change back and forth if there's no friction. So we have the dramatic example of a woman jumping out of a building. If that were to be true, I'd hate for that to happen, but if it were true, originally you have only potential energy. You have potential energy and no kinetic because you're not moving at the very beginning. But as you start speeding up, your kinetic energy increases, but you're not as high off the ground anymore. So remember that potential energy was equal to mgh. However high you are times your mass times 9.8. So 9.8 times your mass is force. So this is newtons. And then newtons times height in meters. That's work. So the work being done on you by the earth is giving you energy. So you have an initial potential energy, no kinetic. It's changed into some kinetic. You still have some potential because you still have some height. You have less height, more kinetic. You're getting faster as you go. More kinetic, less height. Eventually you get to where you have no potential energy at all, but you've got the original amount of energy, only now all as kinetic energy. That's why you would want to stop rather slowly so that it doesn't crush you. I do have to mention the idea of nuclear energy. If you have tremendous amounts of gravity force, so that molecules are so close together that the pressures are ridiculous and the temperatures are insane, then what actually happens is the nuclei of the protons and the neutrons in these materials can rearrange, and the energy that's stored in them, pulling them together, can be released. So this is how the sun works. It's how stars shine. Stars are shining by the gravity pushing materials together and reconverting them into something new. So two hydrogen atoms can be converted into a helium atom, and then helium and hydrogen can be converted into something bigger and bigger and bigger. And eventually, I think the biggest you can change into would be iron. And so stars essentially burn, if you want to think of it as burn the lower elements, making the big elements. But what's actually happening, it's the pressures and the gravity that's pulling it together that reconfigures these nuclei, and you end up with nuclear energy. So, you've seen a nuclear bomb, a picture of a nuclear bomb. You have seen that you can make electricity with nuclear reactors. It's the same idea that as materials are breaking apart, they're reconfiguring and energy can be released as a result. Either way, you're still going to have the same amount of energy at the beginning and at the end. The other thing, of course, is chemical energy like hydrocarbons that can be burned. So you can have gasoline that can be burned in your tank. Well, gasoline was once plants. Anything that's hydrocarbons was carbon-based. So this would be, people who didn't listen to Noah ends up in the bottom of the sea and mud and muck over top of them, and eventually the pressures turn them into oil. That oil then has all the energy that once belonged to the food that these guys ate, whatever dinosaurs were, whatever food dinosaurs ate, one time would eat something else and eventually eat something else, and all their energy is coming from what they ate. Eventually, the last thing would be the plants that grew, and the plants got their energy from the sun. So ultimately, all energy on Earth stems back from radiant energy. So there's conversion after conversion after conversion of energy, but the total amount of energy always remains the same. So what does the law of conservation of energy state? The law of conservation of energy, okay, not mass and energy, states that energy can neither be created nor destroyed, but only change or transform from one type of energy to another.